Hello everyone. I will be presenting a CHI paper, Explore, Create, Annotate, Designing Digital Drawing Tools with Visually Impaired People. I'm presenting on behalf of my collaborators and co-authors, Hari, Brooke, Steve, and Sheila. Some background before I begin. Graphics like maps, diagrams, charts, these are highly useful in classrooms and professional contexts. These graphics combine visual elements and text to convey ideas that are difficult to explain with text alone. For blind and visually impaired people, such graphics are rendered in tactile format, and these are referred to as tactile graphics. The text on them is generally represented in braille. As an example, here I have a tactile graphic that represents the map of North America, and you can also see some of the braille labels that are on the tactile graphic. Unfortunately, to quote National Federation of the Blind, there has been an unavailability of simple devices on which tactile images could be drawn, edited, transmitted, and reproduced. This has prevented people with visual impairments from representing their ideas spatially, doodling or diagramming their ideas, and customizing tactile graphics made by others. There is therefore a need to design better digital drawings for people with visual impairments so that they can create and annotate tactile graphics easily. However, in my study, I'm placing special emphasis on Annotate because there are examples of systems in HCI that have looked at facilitating creation of graphics or consumption of ready-made labels. But annotation and labeling from the user's end hasn't received attention. It is important that we understand how we can extend the functionality of digital drawing tools in this direction. Now, generally, when visually impaired people annotate the graphics, they use braille labels, but this has certain disadvantages. First, too many braille labels introduce tactile clutter. It makes it difficult to tell graphical elements apart from the braille labels. This also limits the amount of information one can present on the graphic. Second, the entire process of creating a label is disjointed from the drawing process. To give an example, a sighted person can scribble their labels as they draw, but a person with visual impairment will have to print the labels using a braille label or use a stylus to punch out the labels on sheets and then place it on the drawing. Here on the right, I have the image of the braille labeler I used to produce braille labels for this study. And it was among the most time-taking things that I had to do. I would have to turn the circular dial on top multiple times to prepare a word, then tear off the label, and then place it on the graphic. So basically, labeling in braille can be a separate and cumbersome process. Now, one way to label the graphics in a more spontaneous manner without adding tactile clutter is by using audio labels. Some companies like Touch Graphics have started creating audio tactile graphics. On the right, I have the image of the talking tactile tablet from Touch Graphics. If the user touches a location on the tactile graphic, the audio label present there will be announced. But again, end users can't add their own labels in this system. Audio is being used for output purposes only and not for input purposes. Therefore, there is lack of research on how to extend the functionality of digital drawing tools for labeling tactile graphics. And in my study, I addressed that gap by answering two research questions. My first research question is what strategies are used by people with visual impairments as they explore, create, and label tactile graphics. Answering this would tell us how braille labels are used during creation and exploration and would allow us to make those strategies possible with audio labels. Plus, observing people's finger movements during creation and exploration is critical to designing recognizable interactions with such systems. The second research question is what are the interaction preferences of people with visual impairments when they create and annotate tactile graphics? This would allow us to design interactions based on end users' preferences. We answered both the research questions by conducting a study comprising 3 tasks with 11 visually impaired adults. 4 of the participants identified as female and 7 participants identified as male. Now I will talk more about the tasks in a bit, but for context, the 3 tasks were exploration of labeled tactile graphics, elicitation of user-defined input commands, and creation and labeling of tactile graphics. With regard to the eligibility, visually impaired adults were eligible to participate. So this included people who rely on tactile and auditory channels to access information. For example, reading in braille or using screen readers on digital devices. Also, participants needed to know how to read braille. Participants were recruited with the help of the NFB and Lighthouse for the Blind in San Francisco. On an average, the study took 90 minutes with each participant, and each participant was compensated with $30 in cash. For the stimuli in my study, I used maps from the Tactile Maps open source set, or TMOS. Parameters on these maps are highly controlled, making them similar in difficulty levels and therefore suitable for exploration tasks. Each map is 12 inches by 12 inches and represents a fictional park. Here I have an example map from the set. There are features like pond on each map, shown in black. There is a walking path on each map, shown by the smooth line that cuts across the terrain. And there are 5 tactile symbols that represent different utilities like picnic tables, playgrounds, water fountains, trash cans, etc. Since in my task 1, I was interested in exploration in the presence of labels, I had to modify the stimuli. So I gave the features of the park fictional names like Larry Trail, Pratt Restrooms, etc. On maps with braille labels, I followed the tactile map convention. The fictional name was abbreviated. For example, Larry Trail was abbreviated to LT, and this was placed on the map as shown in the left image. The braille key was placed to the right of the map, and this had all the abbreviations along with their full names. The paper in white is the braille key listing all the labels. On audio maps, shown here in the image on the right, was represented by a tactile marker. Participants were told if they placed their index finger on the tactile marker representing the audio label and said label, then the label would be read out loud. This was a Wizard of Oz setup, and when participants performed this interaction, I would input to a Python script, and this would announce the labels in synthetic speech. I also had to do a slight modification for task 3. This was the drawing related task. A standard tactile was sized. The map, on the other hand, was square in shape and larger in size. So I covered bottom of the map to make its size equal to an A4 sheet. And this allowed participants to draw things to scale. So on to the procedure and the tasks. I first had 3 tasks to familiarize the participants with the stimuli, apparatus, labels, etc. Next, we had task 1 for exploration of labeled tactile graphics. This was set up as a within subjects experiment. Each participant was presented with 4 maps in random order, 2 with braille labels and 2 with audio labels. They had 2 questions for each map. Again, the order of the questions was randomized. After all 4 maps were presented, participants were asked few qualitative questions about the labels. My hypothesis is that participants would take less time to answer the questions with audio labels, and as a result, they would use audio labels more frequently. In task 2, participants were asked to invent 2 interactions for each of the 4 referents. This was create an audio label, edit an audio label, retrieve an audio label, and delete an audio label. The protocol this task was based on prior studies that have elicited gestures from users. Participants were asked to think aloud as they were inventing the interactions and demonstrate it thrice when ready. In the third task, we wanted to study of labels as well as understand what kind of labels participants actually preferred. So first, they had to draw the uncovered part of the map, and then they had to label the largest playground, pond, and the path. Labeling could be done in braille, audio, or a combination of both. After the tasks, there was a quick demographic section to get details about participants' backgrounds. The quantitative data from first task was analyzed using a mixed effects model. I also had qualitative data from all the tasks. The qualitative data was transcribed and open coded for analysis. So moving on to the findings, which I would talk about task-wise. The first finding from task 1 was that audio labels were significantly more efficient for retrieving information, but participants used more braille labels than audio labels. So my first hypothesis was proven, but the second was not. Here we build on prior work that has shown that audio labels can be more quickly memorized. We show that they are efficient in real-time exploration as well, which isn't surprising. But people tend to read the braille labels a lot. This could be because of multiple reasons, but one of the reasons can be that one would have to switch to a different modality for audio labels. With braille, one continues to rely on the tactile perception to get the information while exploring the map. We also found that participants had multiple strategies for finding the answers to questions with braille labels. We broadly noted 4 different strategies. With audio, on the other hand, we just noted one strategy, which was finding the object of interest and interacting with the audio label below. And while this was efficient, it was also the only way of getting the information. Our third finding from task 1 was about participants' perceptions regarding engagement with the labels. Participants mentioned that braille allowed them to explore independently. So to quote participant 5, I think it's a little bit more of an independent way to explore, to just be able to read on your own in the same way anybody else will be able to read it. So this shows that the participant valued the implicit exploration possible with braille, not having to rely on anyone else or on any kind of technology to read the map. On the other hand, audio was considered passive, where the label was read to the participants. So to quote participant 8, I did not have to worry about going back and forth between the key and the map or having to try to memorize the key before reading the map or vice versa. I just would click on the label, it'll tell me the label, oh, good to know. So it was more passive. Moving to task 2 findings. In summary, total 75 commands were invented by the participants. 49% of these were purely gestural, while 47% were multimodal. That is, these combined gesture and voice phrases to interact with audio labels. I want to discuss the third finding in detail, where we noted that participants prioritized discoverabilities. So we observed object-centric binding of interaction commands. Prior work defines this as commands that are performed close to of interest. In this study, we build on this by reporting a nuanced finding on how participants made efforts to find specific locations on the tactile map before performing their interactions. They wanted to make sure that the audio label was uniquely associated with the object of interest and the system did not incorrectly label something else. They also took care to represent the audio labels with a different tactile marker so that it is discoverable by other users. So we noted a lot of decision making and thinking go into creation and location of interactions on the graphic. To task 3, findings. We noted 5 hand postures and 3 kinds of finger movements that participants used during their drawing. In the paper, these are discussed in more detail. We provide information on how these were carried out, as well as the fingers that were used to perform them. This information will be helpful in designing interactions that do not conflict with users' exploration or creation of graphics. We also noticed that participants tended to combine braille and audio when labeling the graphics. So as seen here, this is the map that participant 6 created, and he chose to label his graph braille and audio. He also used a different tactile marker for audio, represented by the yellow paper. He and many other participants wanted braille labels to present general information, and they wanted audio to give more detailed information. They believed this reduced the tactile clutter and had the potential to keep some of the information universally accessible for people who are deafblind, sighted users, as well as in public places where audio cannot be accessed at all times. Quote participant 1, I would like something that could give information to as many users as possible. There's nothing saying I would not also include some kind of print label with those pieces. So yeah, that way everyone can read it. Based on our findings, we propose 5 design recommendations. However, in the interest of time, I will discuss only 3. First, we recommend providing an overview of audio labels. This would be analogous to the braille key and would make many more strategies possible for the end users as they use audio labels to explore a tactile graphic. Second, we recommend using both braille labels when possible. There is a trend to do away with braille labels completely, but braille offers its own set of advantages. So when possible, both should be used. Braille can be used to present general information and audio can be used to present further details. Finally, with regard to the interactions, participants demonstrated a strong preference for mobile screen reader gestures like double tap, long press, etc. So it would be useful to use these for interacting with audio labels, but care should be taken to consider the hand postures and finger movements from the study to make sure the interactions do not conflict with users' natural finger movements. So this brings me to the end of the presentation. I would like to acknowledge National Federation of the Blind, Lighthouse for the Blind San Francisco, and the Smith Kettlewell Eye Research Institute for their support, and of course, all the participants who made this work possible. Thank you.